All right, AP Stat students, Mount Hood students in particular, because this video only pertains to you. And we're going to do two videos on chapter 26. I'm kind of splitting it up into two so it's not really long. But you can watch them back to back. I'll try to make them not too long. So let's get right into it. And I posted on the Google Classroom some chapter 26 video FRQs number 1. So this is going to be the first video. So you're going to want to use those problems, and I'm going to be kind of clicking back and forth between those two problems. Okay, so chapter 26 is a big chapter, and it's about the chi-square distribution. You can think of like chapters 19 through 22 is all about proportions. Chapters 23 through 25 are all about means, and chapter 26 are all about counts. Counts, which is categorical data. And if you remember categorical data, that's like data in categories. So one example of categorical data would be like eye color, blue, green, brown eyes, eye color. So for instance, what color eyes do you have? Blue, tally mark blue. So that's called a count, a check mark in a category. What color eyes do you have? Brown, check mark. What about you? Brown, green, brown, blue. What about you? Brown. And you collect data, and the data you're collecting is not a number, but a check mark in a category. We call it a count. These little tally marks are called counts, categorical data. That was chapter 3 in our book. Not quantitative, not numerical, but categorical. And chapter 26 is all about this categorical data. And then the special distribution we have for that is called the chi-square distribution. A couple quick things about the chi-square distribution. It's not unimodal symmetric like the normal distribution or the T distribution. It is skewed to the right. Like this. This is the chi-square distribution. And for these chi-square categorical data problems, we will only do hypothesis tests, no confidence intervals, and we're going to get a chi-squared stat, and then the p-value is going to be everything above that chi-squared stat that we get. So that's a chi-squared model, skewed to the right. We're going to crunch out a chi-squared stat, and then we're going to go upper tail, one tail, upper tail test for every chapter 26 chi-square test. And there are 3 tests we're going to do. The first one is called the chi-square goodness of fit test, and that's what this video is on. And then the next 2 are the chi-square test for homogeneity and the chi-square test for independence. And that's what the second video is going to be on. And I really do encourage you guys to read chapter 26. That's even more better than watching this video. This video is going to be just a quick example of how to do it, but you want to read through chapter 26. Okay, so let's just get right into it. So I'm going to go to that problem that I posted, that chapter 26. It was a 2008 free response question. Again, this is in the Google Classroom. I made a special chapter 26 topic, and it's got the chapter 26 video FRQs number 1. It's a number 2 that's going to be for the other video. We're looking at the number 1. And the first one from 2008 says a study was conducted to determine where moose are found in a region. We've got a region. It's got 4 habitat types. We have a burned out area, burned out far away, burned out near the edge, outside the burned area, outside the burned area, not near the edge. There's 4 types of areas in the forest. And then we've got a little table there. And then it gives us the habitat type and then the proportion of total acreage. So 34% of the total acreage is in habitat 1. That's the biggest area. 10.1% is habitat 2. 10.4% is habitat 3. And excuse me, not habitat 1, but habitat 4 is the biggest area because it's got 0.455, 45.5% of the total acreage of this area is habitat type 4. And then we've got the number of moose observed in each habitat type. So 25 in habitat type 1, 22, 30, 40. Okay, and then part A asks, the researchers who are conducting the study expect the number of moose observed in habitat type to be proportional to the amount of acreage of that habitat type. Okay, so is the data consistent with this expectation? They are, they expect the number of moose observed in a habitat type to be proportional to the amount of acreage in that habitat type. So for instance, in habitat 4, that's 45.5% of the total land. So what they're expecting is 45.5% of the deer to be in that habitat. Habitat 2 is 10.1% of the total land. So they're expecting the deer, 10.1% of the deer to be in that area. So in other words, the deer have no preference for the different types of habitats. It's just whatever, however big it is, that's however much deer will be there. Doesn't matter if it's burned out, not burned out. That's kind of their assumption, okay? And that's actually the null hypothesis for these problems. Okay, so first thing you notice about this problem is that it's a categorical data problem. The number of moose observed, 25, 22, 30. So that's categories. Habitat 1 is a category. Habitat 2 is a category. And then 25, you're going check, 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 filling up those categories with all these deer. And it's categorical data, okay? All right, so then what type of test is it for this categorical chi-square test? And there are 3 tests, and the first test is the chi-square goodness of fit, and that is this test. So I'm going to write that down. We are going to do a chi-square goodness of fit test. Okay, and that chi, it's like this Greek letter, capital, it looks like an X. That's pronounced chi, C-H-I, chi-square, goodness of fit test. Why a goodness of fit test? Because we want to see if the moose fit those percentages, the 34%, 10.1%, 10.4%, 45.5%. Do the number of moose we observed fall into those percentages? So is about 34% of the moose in that habitat 1, which is 34% of the acreage, is about 10.1% of the moose in habitat 2, which is 10.1% of the acreage. So do the actual observed moose fit those percents for the acreage? Okay, now so then what's the null? What's the alternative? And the null for these goodness of fit tests is always the same, and it is that the data fits. The null is that the data fits, and the alternative is always the same. It's that the data does not fit. Okay, and we have to write it in context. So let me look at the problem. So the null that the data fits, we're going to say the moose observed in each habitat type is proportional to the amount of acreage in that habitat type. All right, the moose observed in each habitat type is proportional to the amount of acreage in that habitat type. So if habitat 1 is 34% of the total acreage, then we would expect 34% of the moose to be there. The moose fit those percentages, okay? And then the alternative would be then the moose observed in each habitat type, the moose habitat type is not proportional to the amount of acreage in that habitat type. Okay, so the exact same thing, except it's not is proportional. It is not proportional. So the moose might prefer, you know, the inside the burned area near the edge area. So more moose would congregate there, and that's what we want to see. Does the moose observed fit those percentages? Okay, and we're going to do a chi-square goodness of fit test. Let's check the conditions, and these are actually pretty easy. Okay, one, was it a random sample? And it says using an aerial survey. It just says using an aerial survey, so it doesn't really talk about if it's a random sample. Let's see how do they check their conditions here? Because we're going to test. Oh, the stem of the problem stated that the conditions for inference are met. Okay, so I guess assume the conditions are met for part A. So we actually didn't have to do that. We're going to do that here though, even though the problem says that they are met. So was it a random sample? And it does just say that we observed them from the sky. So again, this is kind of a weird problem there. But how about this? Random sample, I'll put a question mark and I'll say, we'll assume the 117 moose observed are representative of all moose, right? The 117 moose that we tallied into these habitat types, well, hopefully they represent all moose. That's really what the random condition is checking for. Okay. Next up, let's double check these here. So random condition, 10% condition, and it actually looks like we do not have a 10% condition here. So, oh no. Blah, 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 blah. Okay, great. Random condition. Okay, that's good. We actually just do the random condition here. That's great. Okay, next up, the sample size condition, the expected cell frequency condition. Expected cell frequency. I'm getting this all from page 620 in your book, by the way. The expected cell frequency condition. And that's like our sample size condition. And that says that there must be more than 5 expected, 5 in each expected cell. Okay, we're gonna make those expected cells. We'll get there soon. Okay, so let's kind of put the conditions on hold. And we'll come back to the conditions, finish these up. So here's where I'm at. Chi-square goodness of fit test. The null is that the moose observed in each habitat is proportional to the amount of acreage in the habitat type. And the alternative is that the moose observed in each habitat type is not proportional to the amount of acreage in that habitat type. Okay, all right, so let's do it now. Let's actually do the test. Let me get the problem back up here. And you could see, I'm just looking at this problem, right? And we could see that like 34% of the acreage is habitat 1, but it's only 25 of the moose are there. Seems like it should be more than 25. Where in habitat 3 is only 10%, but 30 moose. So 30 moose, there are more moose in habitat 3 than habitat 1, 30 compared to 25. But habitat 3 only has 10% of the 10.4% of the land, and habitat 1 is 34%. And that's telling me that this data doesn't fit very good, right? I would expect this 30 to be lower because the 10% is lower than 34%. So just kind of looking at it, I'm thinking we might reject the null and say that the moose we observed is not proportional just by looking at it. Okay, so what do we need to do? We need to get the chi-squared stat. Now there is a calculator command for this, but first let's work through it by hand, okay? And then I'll show you how to do it on the calculator. Because on the Albert assignment, you're gonna have to find the chi-squared stat by hand. Okay, so here's the chi-squared stat. This is on your formula sheet, and it is the observed minus the expected squared divided by the expected, and then we got to sum that up. Okay, so this is a formula on your formula sheet. The chi-squared stat is the observed value minus the expected value squared divided by the expected value. And then you sum them all up. Okay, so what are our observed values? What did we observe? Well, we observed 25 moose in habitat 1, 22 moose in habitat 2, 30 moose in habitat 3, and 40 moose in habitat 4. That's what we observed. Okay. Okay, great. Well, what would we expect? What would we expect? And you're going to have to crunch out these expected values by hand. Okay, now remember there were 117 total. There were 117 total. So if the moose had no preference, if the moose just kind of spread out equally, right, we would expect 34% of the 117 to be in habitat 1. So take that total and times it by 34%. So 117 times 34% is 39.78. And that's what I would expect. We observed 25 in habitat 1. We would expect 39.78. Because 39.78 is 34% of 117. So that's okay. So now let's do 10.1% times 117. 10.4% times 117. So let's get all these expected values. So 117 times 0.101 for habitat 2 is 11.817. 117 times 0.104 for habitat 3 is 12.168. And 117 times 0.455 is 53.235. All right, so those are my expected values. Those are what I've observed. Habitat 1, 2, 3, 4. This is what I would have expected if it matched the percentages for habitat 1, 2, 3, 4. That's my observed. That's my expected. Let me just quick double check that just to make sure I didn't copy those down wrong. Hold on. Bear with me here. Okay, those values look good. 39.7, 11.817, 12.168, 53.235. Great. Okay, so let's get the chi-squared stat. Here we go. It is the observed. I'm just going to go down the line. So first habitat 1, the observed 25 minus the expected 39.78 squared divided by the expected 39.78 plus. Okay, so that's what I got for the first one there. The first little bit in my chi-squared stat. The observed 25 minus the expected 39.78 squared divided by that 39.78. Do that for all of them. So the next one is the observed 22 minus the expected 11.817 squared divided by the expected 11.817 plus the next one, habitat 3, is the observed 30 minus the expected 12.168 squared divided by the expected 12.168. And the final one, the final habitat, is the fourth habitat is the observed 40 minus the expected 53.235 squared divided by the expected 53.235. Okay, now I got to crunch all these out. I got 4 numbers, so give me a sec to crunch these out. You guys crunch them out too. You're writing this down, right? So I got 5.4914 and 8.775 and 26.1325, and the last one 40 minus 53.235 squared divided by 53.235 is 3.2904. I'm going to quick double check that just to make sure I don't have any minor math errors and have to do this video all over again. Actually, they don't have all that crunched out. That's okay. Okay, I think we're probably good there. And we're going to do it on a calculator anyways after this, so we can check it that way. Okay, so I got all those values. That's my work there, everyone. Crunching out the chi-squared stat, the observed minus the expected squared divided by the expected. So these four values make up my chi-squared stat. Okay, so I'm going to add all those together, and that's going to be the chi-squared stat that we're going to use. And you got to give that. That's one thing you got to give if you're doing a free response. And I got 43.6893. Double check that. 43.6893. Woo, great. Okay, so our chi-squared stat for this problem is 43.6893. Okay, what do we do with that now? What do we do with that chi-squared stat? That 43. Well, you guys remember, that is this number, and then we're going to go above that to get our p-value. This is the chi-squared model. It's a skew to the right model that we use for this categorical data problems, okay? So what we're going to do now, we want to know the probability above that. So not normal CDF, not TCDF. We're going to use chi-squared CDF. Chi-squared CDF, which is a command on our calculator. So second distribution, and there it is. It's number 8. Chi-square CDF. I'm going from the chi-squared stat to the probability. I'm getting the p-value right now. Chi-squared CDF. Enter. Okay, what's the lower bound? Well, that's our 43.6893. 43.6893. What's the upper bound? Now, the upper bound is not going to be 99 now. See how that chi-square stat is pretty big. It's 43. You know, that's a big number. So now we're not going to use 99 for our upper bound infinity. We always use 999. So that's a key difference. 999 for your upper bound. That's for all these chi-square tests. 999. And then the degrees of freedom. Yes, the chi-square model does change depending on the problem. Okay, so what is the degrees of freedom formula for a chi-square goodness of fit test? And the degrees of freedom is categories minus 1. That's your degrees of freedom. So here are two important formulas for you. Okay, there's your chi-squared stat. This is your degrees of freedom. For goodness of fit, the two other chi-square tests, the homogeneity independence, it's a different degrees of freedom formula. But for goodness of fit, it's categories minus 1. So we had 4 habitat types, 4 categories. So 4 minus 1 is 3 degrees of freedom. So this is what we put into our calculator. Chi-square CDF, our chi-squared stat, comma 999. It'll always be upper tail, always be 999, 3 degrees of freedom. And that gives us our p-value of 1.757 times 10 to the negative 9. 1.757 times 10 to the negative 9. Very low p-value, right? Almost 0. 0.000000. That's the p-value. Okay, that 1.7 value. Let me see if they got the same thing. They did. Great. Okay, and so then we would state our conclusion. We would say, with a p-value so low, we reject the null. There is sufficient evidence for the alternative. There is sufficient evidence that the moose observed in each habitat type is proportional to, is not proportional to the amount of acreage in that habitat type. Meaning the moose just don't spread out evenly, right, among the 4 habitat types. They go somewhere specifically. They prefer a specific habitat type. Okay, let's finish this up. Now this is the do it by hand. This is all my work for doing it by hand. Okay, now guess what? There's a calculator command for this. Okay, so now I'm going to go back to this page. Here's how I would be like doing it on the AP test. And now I'm going to show you just how to finish it up or just do it on your calculator. Okay, so we were at the expected cell frequency condition. You have to have more than 5 in each expected cell. And check it out. We crunched out our expected cells. Those are these guys. The 39.78, the 11.8. So we need to show those expected cells. Okay, so I'm going to show them. I've got 39.78, 11.817, 12.168, and 53.235. And a lot of times we write them in like kind of like a brackets, like a matrix. Okay. And are they all greater than 5? The expected, not the observed. We're only talking about the expecteds here. And yeah, they're all greater than 5. So I'm going to give that a check, and I'm going to say all expected cells are greater than 5. And I think it's greater than or equal to 5. So you could have 5 in there. Okay. And then the final condition is the counted data. The counted data condition. And again, you're reading all about this in chapter 26. I got chapter 26 right here, page 620. Okay, it goes through all these conditions. The counted data condition is like the paired data condition for matched pairs. You're basically just saying the data is paired. So we're just saying the data is categorical. We're confirming that the data is categorical. They're counts in categories, check marks into categories. So for the counted data condition, I'm just going to say the data are counts in categories, give them some context, in categories by habitat type. Check. The data are counts in categories by habitat type. They're counted, it's categorical. Check for counted data. Check for expected cell frequency. They're all greater than 5. You've got to show the expected cells. Got to show that they're all greater than 5. And then with the random condition, it said they observed it from the, so we'll assume that the 117 moose are representative of all moose for the random condition. Check, 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 all conditions met. Great. Okay, so now I named it. I wrote my hypotheses. We checked our conditions, random, expected cell frequency, counted data. Now we're just going to do it on the calculator. Okay, so if you don't want to do it all by hand, even though you could, right, you could just do it on the calculator. Here's how you do that. Go to your list, stat enter to your list 1, list 2, clear out list 1, clear out list 2, and we are going to put the observed into list 1 and the expected into list 2. So for list 1, I'm putting in the observed, 25, 22, 30, 40. And then list 2, I'm putting in the expected, 39.78, 11.817, 12.168, and 53.235. So that's what I have in my list. List 1 is the observed. List 2 are the what I would expect. Okay, and you can see how different, 25 and 30 and almost 40. That's different. Look at column 3, 30 and 12. So you could see why we rejected the null here and said the data does not fit, right? Okay, so then you go to, now let's do the test. Go to stat, over to test, go all the way to the bottom. So again, you go to the stat button, go over to test where you got all of our tests and intervals. You go all the way to the bottom, and we want the chi-square GOF test. Stat, test is all our 1 proportion z test, our 2 sample t interval, all the way to the bottom. Letter D, the chi-square GOF test. Let's do that. Enter. Chi-square GOF test. My observed is in list 1. My expected is in list 2. The degrees of freedom is 4. Categories minus 1. Actually, that's not 4. It's 3. Excuse me. Put in that degrees of freedom. Categories minus 1. 4 minus 1, 3, and calculate. And bam, there it is. There's our 1.756 times 10 to the negative 9. So what do you give them? You give them the chi-squared stat, 43.689. You give them the p-value, 1.757 times 10 to the negative 9. And you give them the degrees of freedom. Gotta give them the degrees of freedom is 3. So there you go. That's how you do it quick on your calculator. Okay, just chi-square GOF test. Very easy. Okay, and then state your conclusion. With a p-value so low, we reject the null. There is sufficient evidence for the alternative. There is sufficient evidence that the moose observed in each habitat type is proportional to the amount of acreage, is not proportional to the amount of acreage in that habitat type. Done. And that's a chi-square GOF test, okay? You can see part B says, in this problem, says, relative to the proportion of total acreage, which habitat type did moose seem to prefer? Which did they seem to prefer? Okay, now here's what you can look at. You see when we did it by hand, and when we crunched it out, we had like this 5.491, this 8.77, this 26. Whoa, huge number, 26. See that? What numbers made up this, our 43.689 chi-square stat? Well, these 4 numbers made up this 43. Which contributed the most to this 43? We've got a 5, we've got an 8, we've got a 3, we've got a 26. The 26, what was that 26? That was habitat 3. Everyone see that? 26 is habitat 3. We expected only 12. We got 30 in there. So they really liked habitat 3, the moose. And we can tell by this number, and they wanted that in your answer to show your work, that number. To show you on the calculator where you can get those numbers, see this CNTRB. If you scroll to the right, see that 5.4, keep going. There's your 8.7, keep going. And then here's your 26, your big one, 26. So you can get those numbers off your calculator, the 4 values that make up your chi-squared stat. And you can see that 26 contributed the most to the chi-squared stat. And that's what the moose liked the best. They liked habitat 3 the best because we only expected 12 to be in there, but 30 were. So the moose liked that habitat 3. So that's part B, okay? Great, there you go. Okay, how are we doing? I did have another one on here, this 2003 one. Let's just quick look at that. I know I don't want to spend forever here, but you got this spinner wheel. Scroll down, and we got another FRQ here. And it's like it's got 4 areas: skunk, $100, $200, $500. It's like a game of chance. You spin the wheel. It's got a little picture there. You guys are looking at that now, I hope. Okay, and then this is the data. Let's just jump right to part C. And then here's the observed, right? 33 skunks, 21 $100, 21 $200, 26 $500. And the question is in part C, says, sorry, I lost it here again. Okay, based on the data, can you conclude that the 4 outcomes on the wheel were not equally likely? So is this wheel like weighted or something, right? Are they equally likely? The possibility you get a skunk or win a 500 or win 100, are they all equally likely? This is what we observed, right? Okay, so if this is the observed, if we observed, 33, 21, 20, 26, what would we expect? What would be the expected values if spinning this wheel, it was like 25% for all 4 areas, right? What would the observed expected be? We'll add those up, right? Add up 33 plus 21 plus 20 plus 26. I got 100. That's nice. Divide it by 4. 25, 25, 25, 25. All right, that's what we would expect. if it was a fair spinner, right, we would expect 25, 25, 25, 20. Well, what do we get? Well, we got 33 skunks. That's is skunk weighted heavier, or is that just due to sampling variability? Right? It's not going to be perfectly 25, 25, 25, 25 every 100 spins, right? Even if it was fair, right? So it's going to vary a bit, but did this vary so much that we conclude that it's not equally likely? So so we're asking, how does this data fit this? So we're going to do a chi-square goodness of fit test. Chi-square goodness of fit test. Okay, what's the null? Well, the null is that the data fits. The data fits. The null is that that the outcomes are equally likely. The outcomes are equally likely. So the wheel's outcomes are equally likely. The data fits. The observed fits the expected. The wheel's outcomes are equally likely. And then the alternative would be that the data does not fit. That the wheel's outcomes are not equally likely. Okay, there's your hypotheses. Okay, what about the conditions? Was it a random sample? Were these 100 spins randomly? Was it just one person doing it? Or you could say, well, hopefully these 100 spins are representative of all spins. Expected cell count, greater than 5? And you have to show the expected cells. Are they all greater than 5? Well, we got 25, 25, 25, 25. Expected, not observed. The expected, 25, 25, 25, 25. Yes, they're all greater than 5. Check. Counted data. Are these counts and categories? Yes. The data are counts and categories by area of the spinner wheel that you got. So check, check, check. All conditions met. Okay, do it on your calculator. So put the data in list 1, list 2. So observed in list 1. Clear them out. So 33, 21, 20, 26. Expected in list 2. And that's just 25, 25, 25, 25. Okay, we don't have to do the observed minus expected square divided by the expected. Do it again 4 times, sum them up. You could, but you could also just go stat test to chi-square GOF test, enter, observed in list 1, expected in list 2, degrees of freedom. It happens to be 3 again, right? The 4 categories minus 1, degrees of freedom. So it's 3 again for this problem. Calculate. Bam. What do you give them? The chi-squared stat, 4.24. The p-value, 0.237, pretty high. And then the degrees of freedom, 3, 0.237. So that's what you give them. Give them these 3 things. And then state your conclusion. With a p-value so high, 23.7%. With a p-value so high, we fail to reject the null. There is not sufficient evidence that the wheel's outcomes are not equally likely. So even though we got 33 skunks, right? We didn't win any money when we had expected 25. It seems like that might be unfair, but we didn't conclude that. And we concluded that there's a 23% chance that was just due to random sampling variability. So we fail to reject the null. There is not sufficient evidence that this spinner game is not fair. We can't conclude it's not fair, even with our 33 skunks, according to the chi-square goodness of fit test. So that's just a quick another one for you, okay? All right, great. Thank you, guys. 2 examples from chapter 26, the chi-square goodness of fit test. I'm going to make another video about the chi-square homogeneity and independence test. So that'll be another video posted. And then, of course, read through chapter 26. It will be very helpful for you. Thank you very much.